Okay, good morning everyone. Can you see me? Can you hear me? Give me a thumbs up if you can. All right, good morning. How are you guys doing? Thanks for joining in the early morning. So we're going to start. We did our intro to the course with 2 lectures. We're going to start the main content right now. Although I should say it's going to be pretty light on the technical side. We're just going to, get some of the main key definitions out of the way this week. And then I think starting next week, things are going to get much more interesting. Okay, so we're doing strings, encodings, and problems. Let me start the lecture actually with a philosophical question. Okay, why not? So the question is, what makes you, you? What makes me, me? Okay, so I'm looking for some, fundamental answer here. So one reasonable answer might be, well, my body makes me, me. And that's reasonable, but if you think about it, well, even if you didn't have your arms or legs, you could still say that, that would still be me, the same person. So then you might say, well, okay, maybe my brain is what makes me, me. Well, then in that case, I would ask, what about your brain makes you, you? And you might say, well, the atoms that make up my brain is really me, what makes me, me. But then I would object kind of to that as well, because it turns out every 7 to 10 years, the atoms in your body are completely replaced. So the 10 years ago me had a completely different set of atoms than the current me, okay? So it cannot be the actual atoms in some sense that make you really you. So then what might it be? What could it be? If it's not the actual atoms, what makes you you? Well, I think a reasonable answer is, well, the particular configuration of the atoms that makes you you, and that's what we would really call information. The information in your brain, the thoughts, the memories is really what makes you you. Now that brings up other interesting philosophical questions. So if it's the information in your brain, what if I were to copy that information? Okay, if I could, and create another sort of, brain. Then am I copying you? Now, is there 2 of you? Are the copies the same or are they different actually? So that raises a very interesting philosophical question. Now, it turns out in quantum physics, there's a law that says, that is called the no cloning theorem, which says that you cannot copy arbitrary quantum information. It's just not allowed. The universe does not allow you to copy quantum information. So if what makes you you is actually quantum information, then the previous problem goes away, right? Copying you. So that's very interesting. Anyway, so I just wanted to give you a few questions like this to think about. Now, why am I talking about information right now? Well, what did we say? So for the next few chapters, our goal is going to be to understand this thing that we call computation, right? So what is computation and what basic properties does it have? And we said, look, if you want to understand something better, one of the best methods, the most reliable methods we have is, mathematical modeling. You create a mathematical model for the thing that you want to understand, with formal, precise definitions, and then you can rigorously, logically analyze it, prove new properties and truths about this thing. And this is, of course, what we will do for computation. So this is computation, and now the first piece of the puzzle here for us is going to be, let's understand what we mean by data or information, right? How do we mathematically represent data or information? Okay, so this will be basically the topic of this lecture. And then once we have that, we can start moving deeper into more interesting components of computation. Okay, but this is a natural place to start. Good. Now let's think about this. What is information? Now information is actually a tricky, subtle concept. And I think there are at least a couple of reasons for this. For one, it's actually an abstract concept. Information can be pretty abstract and hard to wrap your mind around. And two, it can mean different things in different contexts. So if a physicist uses the word information, they might mean something. Usually it will be related to the notion of entropy, for example. But when a mathematician uses information, they might mean something slightly different. When a computer scientist uses it, they might mean something slightly different. So it can mean different things in different settings. Now, let me tell you briefly what information is physically. This is not really necessary for us, for our purposes, but I think, for your general culture purposes, I think it's a good idea. Just think about, physically what information means. And then we'll talk about how we can represent it, mathematically. So physically, information is a physical property of physical object systems. Similar to like how mass is a property of physical objects or systems, right? And what does information measure? Information measures the number of possible states a system or object can be in, okay? So if a system has only one possible state, okay, then it has, we'll say, zero information. It's just constant. There's nothing else. It doesn't give us any information. So the lowest amount of information in some sense is a system with two possible states, okay? And when it has two possible states, then we'll say that it has one unit of information, and that unit we call a bit. It has one bit of information when we have two possible states. You can have, less than one bit of information if you consider a probabilistic system, right? So if you have a system, two possibilities, let's say A and B, but the probability of state A is 0.999999, and then the probability of B is very, very small, then it's almost like a one-state system, but not quite a one-state system. So in this case, the information here would be actually close to zero amount of information. So that's just a side remark. So you can get information between 0 and 1 as well. It's not just like 0, 1, 2, and so on. Okay, so that's information. Now, when we think about information, even though it's a physical property, we kind of like to think of it in the abstract. Okay, so if a system has two possibilities, two possible states, then we can think of that as 0 representing 0 or 1, on, off, true, false, open, closed, doesn't matter. And if there is another system with two possible states, from an information perspective, we don't distinguish them. They're kind of the same, right? So even though physically they might be completely different systems, from the perspective of information, if they both have two possible states, then we don't distinguish between them. So we think of information in this abstract way. Information, how can we represent it mathematically? Well, if a system has k possible states, let's say it has 251 possible states, well, we could represent it with the numbers 1, 2, 3, all the way up to 251, right? So that would be a natural way to do it. Another way to do it would be to represent it as a sequence of bits, zeros and ones. And that's kind of nice. Like if a system has 2 to the n possibilities, then we can represent it with a sequence of n bits, as you know. And that's kind of nice because then it also tells you like the amount of information that's present in that system. And this actually view of representing information as a sequence of symbols, as a string like that, is actually very nice. It comes very naturally, very intuitively for us, right? So why do you think that is the case? Why is representing information with like strings? It doesn't have to be necessarily zeros and ones. You can use other kinds of symbols. It's very intuitive and comes naturally to us. Why is that? Anyone have a guess? Yeah, language words, right? So that's exactly right. So we have already we already represent information with strings to communicate with each other. We are computers, right? So when I want to communicate to you, you're a computer. Well, we have a system for it. And our system, a nice system that we have for communicating information uses language and words in that language, right? So how we represent information is like, for example, in written communication, we have some concept that we want to communicate, we have a corresponding word. So we sort of encode the object, what we're interested in, with a string, a word, over some alphabet, right? So since a string representation of information is very natural and intuitive for us because we use it ourselves, it's also, that means it's a good choice to mathematically represent information in this manner as well. Then, when we mathematically analyze things will hopefully be more intuitive, okay? So now, in this particular case, we use the English alphabet. This is the English alphabet, but, I could have used the Turkish alphabet to also encode information. It has more letters. So now you might ask, what if we had more symbols in our alphabet, or what if we had less symbols? Does that change things? Are there concepts that I can encode in Turkish that I would not be able to encode in English, for example? Well, I think your intuition would say, no, that shouldn't be the case. Another example, you can look at like binary alphabet, just two symbols. And, if you have some computer science programming experience, probably that in your computer, everything is represented as a sequence of bits, right? So the alphabet should not matter. And we'll come back to this question. I'm not going to, really dive into it just right now, but I just want to keep that in the back of your mind. Okay, so now let me make some formal mathematical definitions here, okay? So I'm going to define the concept of an alphabet. And when I use now this term alphabet, I don't mean like, in the English speaking, colloquial sense alphabet. I mean, this is now a mathematical definition of the term alphabet. And the mathematical definition of this term alphabet is any non-empty finite set, you can consider it to be an alphabet, okay? And then the elements of that set are going to be called symbols or characters in the alphabet. Now, we usually denote the alphabet using this symbol sigma. Maybe kind of unfortunate, you might say, because we use these capital sigma to denote sum operation. But, for us, most of the time, sigma is going to denote the alphabet, okay? So the symbols, so the elements of the alphabet are the symbols, characters, and we allow any non-empty finite set. That gives us flexibility, really. So I can use bits, zeros and ones if I want. I can use A, B, C, D, E if I want. I can use other symbols if I want, So that flexibility is nice. Now, this other definition, and again, a mathematical definition for the concept of a word string, is that a string is a finite sequence of symbols from sigma, from the alphabet sigma, right? So, and we're going to usually denote it like this, A1, A2, up to AN. So this string has N symbols, and each AI is a symbol, okay? And now, side remark, the definition of a string of words can sometimes be given, can allow infinite length strings as well. But for now, I don't want you to worry about this at all, right? So for 3 weeks, we won't, ever mention or talk about infinite length strings. So whenever I use the word string or word, you should assume by default that I'm talking about a finite length string. And if I want to talk about an infinite length string, then I will explicitly say it. I'll say this is an infinite length string. But if I don't say infinite length, then you should assume it's by default finite. Okay, so here are some examples, some strings over the alphabet 0, 1. So we have like the string 0, string 1, 0, 1, and some other string here. Now, what's an educated guess for this one? What's this? Epsilon. Yeah, exactly. It's the empty string, right? Why do I need a symbol for the empty string is because, well, to represent my strings, to denote my strings, I'm not using quotation marks, right? So if I was using quotation marks, then I could just like put 2 quotes and then that could be the empty string. But since I'm not using quotation marks, in my notation, the empty string would be just like nothing, right? And then that will be very confusing. So we need a symbol for the empty string, and that's epsilon. Here are some strings over another alphabet. The alphabet is A, B, C with the symbols A, B, C, and here are some strings. Okay, so hopefully this is all intuitive. The length of a string S is exactly what you expect. It is the number of symbols in S, and you have the absolute value sign to denote the number of symbols in S. Okay. So now sigma star is an important definition. It's the set of all finite length strings over the alphabet sigma. Okay. So here's an example. 0, 1 star, for example, would be consisting of the empty string, the strings of length 1, so 0 and 1, strings of length 2, 0, 0, 0, 1, 1, 0, 1, 1, strings of length 3, and so on. Now, this is an infinite set, right? So even though every element, every string in the set is a finite length string, this set of all finite length strings is an infinite set itself. And if we have just like one character, this is like a unary alphabet, one character, then, you get epsilon A, 3 A's, and so on. And again, you see that this is an infinite set. So this shows you that for any sigma, for any alphabet, sigma star is an infinite set. Why? Because sigma, as I defined it, it's a non-empty finite set. So at least it has one element. And even when it has one element, one character, it produces a infinite set. Okay. So now let's come back to this idea of encoding scheme. So like we talked about in English, we have a way to encode information using strings. And now what I want to do is define this thing mathematically for us so we can make use of it. Okay, so yeah, how do we want to define an encoding scheme now mathematically? So we're going to get inspiration from English perhaps, but actually we will make improvements to it, okay? We don't want to necessarily use English or what English has used, because there might be some undesirable properties. So let's motivate this mathematical definition with some questions. Okay, so first question is, does every object have a corresponding encoding, let's say in English, right? Or should we want, or would we want that every object has a corresponding encoding? And I think the answer should be yes, it should be sort of like a complete in some sense, like for every object, we should have a corresponding encoding. And if we assume that every object has a single string encoding, one string encoding, what does that tell you about what kind of a mathematical object an encoding is? What is the mathematical object here? So I'm seeing bijection, I'm seeing mapping, function, injection. Okay, so the majority vote is here the correct one. It's only right now, all I'm saying is that it's a function. I'm not making any claims about whether it should be injection, surjection, bijection, right? If for every object I have a corresponding string encoding, this is a function, a mapping from the set of objects to a set of strings. Good. So now we know sort of mathematically we're talking about a function. Now the question, comes to what your guys were getting at, some of you. Is it an injection? Can two objects have the same encoding? Can two objects map to the same thing? And this is the question of asking whether it's an injection or not. Now in English, definitely no, right? So if I wrote the word orange, then you would not know whether I am referring to the color orange or am I referring to the fruit orange. So that's not injective. On the other hand, I don't think this is a property that we would want in our encoding. So that creates an ambiguity, which is not nice, right? So when I write a word, I want you to know exactly what I mean by that. So I think we want an injective. So here we're not gonna do what English or human language does, and we're gonna actually go with the more desirable property of injectivity. Now the third question is, question about surjectivity, right? Does every string correspond to a valid encoding? Okay. And in English, this is definitely not the case, right? So if I take some random symbols, then, it's very unlikely that it's going to correspond to something that is meaningful. It's going to be gibberish. And in our case as well, mathematically, we will follow the same strategy. So we will not insist that every object, every string is some encoding of some object. Okay, it doesn't need to be surjective. That's fine. So now, given these, here is our definition now for an encoding of a set. Okay, so given some set A of objects, an encoding of the elements of A is an injective function, right? Doesn't have to be surjective. Injective function from the set A to sigma star finite length string, the set of all finite length strings. Okay. The encoding of A, we're going to denote it using these angled brackets. Okay, so this here denotes the encoding of A. It's a convenient notation that we're going to use a lot, actually. Now, the way to think about encoding, the way I like to think about encoding is like a labeling mechanism. Okay, so you have some object. The encoding of A is some kind of a string label, a unique string label for it. You can think of it like as a barcode, if you will. And in fact, whenever you talk about injections or whenever I hear injection, I always think of it as some kind of a labeling mechanism. Okay, so if you have an injection from a set A to another set B, I think of that as a labeling of the elements of A, a labeling mechanism of the elements of A, using the labels in B. Okay, I think of B as the labels. And why I think of it this way? Because, injection, what it means is that every element is going to have a unique label, right? No two different elements are going to have the same label. And that's exactly what labels should be, right? It should be unique so that you can identify what the original element is from the label. Okay, so that's, I think, a good way to think about always injections. It's like a labeling mechanism. So now let's do some examples. The natural numbers. Sigma is 0, 1, 2, 9. This is like a way we actually communicate natural numbers to each other, right? We use this alphabet. Now, question, why do we use this alphabet? Why does our alphabet have these symbols? Or maybe why does it have 10 symbols when we communicate natural numbers? Yeah, exactly. So the only reason that we have 10 symbols, we use 10 symbols to communicate numbers, is that we have 10 fingers. If we had less fingers, we would use probably less symbols. If we had more fingers, we would invent new symbols and add it to our alphabet and communicate it like that. It turns out to be a convenient way to represent things. So now here's an encoding of the number 36. Well, it's just the word 36. Now here I am using quotes on the right-hand side here to denote the string because I want to make a distinction between two different types of objects. On the left-hand side here, this 36 is of type natural number. This is a natural number. This 36 here on the right-hand side, this is a string. It's a sequence of symbols. So to make that distinction clear, I am using quotes to denote that string. Usually we don't use quotes to denote our strings, but in this case, I am using it just to make it clear that these are different objects. Okay, good. So that's that. And in using the binary alphabet 0, 1, 36 can be represented as 1, 0, 0, 1, 0, 0, right? Just the usual binary representation. Now, what if we had unary? Well, okay, no problem. I can put like 36 ones in a sequence, and that will be in the unary alphabet, or good representation. Okay, so now again, this question, does sigma affect encodability or not with unary alphabet? Hold on to that question. I will come back to it. Let's look at the integers. If we use the integers, then I'm going to add one more symbol. The way we communicate negative numbers, we add this negative sign. And like negative 36 can be like the sequence of symbols, minus 3 and 6. Okay. If we are using now binary, how can I encode integers with binary alphabet? What would be a trick? 2's complement. Yeah, so there are various ways you can do this. Like maybe the simplest one that you can do is you can designate the first symbol as the sign symbol, right? And you can say, okay, if this is a 1, that means it's a negative number. If this is a 0, then it's a positive number. So that's the first symbol is always indicating the sign of the number, and then what comes afterwards is the number, the binary representation of the number. Okay, now what about unary? Can we do it? You know, take a moment and think about it and see if you can come up with an idea on how to do this. It's a good exercise. Okay, what are some other examples? Let's look at tuples and with 2 like natural numbers. And in this case, I'm gonna like add another symbol, hashtag, as a separator. Okay, so I'm gonna encode the tuple 3,36 as 3 hashtag 36. So the hashtag serves the purpose of the comma. And just a small notational thing, when we encode tuples, we usually get rid of the parentheses outside here, these ones, and just write it like this, 3,36. You know, it's redundant in some sense to put those outside parentheses, so this is the notation we use. Now, how about if we wanted to do this in binary? How can we do it? And I guess my question is, in general, what would be a good strategy to go from a large alphabet to the binary alphabet? Yeah, encode the bigger alphabet with the smaller alphabet. Exactly. So I'm going to take, the idea is to take the symbols here, right, for example, and encode it in binary, each one of those symbols. Encode all the symbols above using 4 bits. Now, why do I need 4 bits? Well, if I have 3 bits, with 3 bits, I can represent 2 times 2 times 2, 8 different possibilities. But I have more than 8 symbols here. If I have 4 bits, I have 2 times 2 times 2 times 2, 16 different possibilities that I can represent. And that's sufficient, right? I have here 11 symbols. So with 4 bits, I can represent these. So this could be, for example, your encoding of each symbol in the larger alphabet with the binary alphabet. And once you have this, then something like 3,36, what is it? Well, you can see now 0011, that's the 3. Then I have the hashtag symbol, so that's 1010. And then I have 0011, which is the 3 again, and then finally the 6. Okay, so you can do it this way. And this is, you know, not always the most optimum, but maybe you can get a bit more clever with this. But this is definitely good enough for our purposes. Okay. How about something more interesting? All undirected graphs. Is the set of all undirected graphs encodable? So here's an undirected graph, G. So how do we encode it? So here's a good way, I think, to think about when you're thinking about whether a set is encodable or not. Here's a trick that sort of you can use to gain intuition about this. Suppose that you're trying to, in this case of undirected graphs, you're trying to communicate the graph to your friend over Messenger. Okay, so you can only use text. So if you have a graph, some arbitrary graph, can you always communicate that to your friend over Messenger? Okay, and how would you do it? If you needed to do that, how would you communicate a graph to your friend over Messenger? Yeah, you can, use the adjacency list, or, what I would do is I would just write down the vertex set and the edge set. I would say, look, here's the vertex set of my graph. Here's the edge set of the graph. I would send exactly this text over to my friend over the Messenger, and then say, look, this is my encoding, and the alphabet is going to be whatever symbols I used here, I'm going to use as the in the alphabet, right? So you have the digits, you have the comma sign, you have the curly brackets, you have V and E. You don't need the V and E and stuff, but who cares? Add them in, and that can be your part of your alphabet as well. So any graph now can be, represented like as follows, right? And so, so that's a good way to think about it. Can you actually, how, as we humans, when we are communicating these objects to each other, how are we doing it? And if we're able to communicate it, then it's encodable. How about all Python functions? Is this encodable? Right, here's a Python function. And yes, right, I mean, I just how do I encode it? What is the encoding? Yeah, you can use ASCII. I mean, I just wrote it down for you. I communicated a Python function for you already, right? So the encoding is exactly what you see on the screen, whatever symbols that we would need to write down a Python function. We can use that alphabet, and every Python function, importantly, is a finite string, right? So we cannot have infinite length programs. So this is also encodable. Once again, just think about how we communicate these things with each other, and that gives you the right intuition. Now, does sigma matter is now the question. Going from, let's say, a large alphabet with K symbols down to a binary alphabet with 2 symbols. Well, as we said, the idea here is that you can encode every symbol in the larger alphabet using T bits, where T is what? About log base 2 of K, right? So the ceiling of log base 2 of K. So that's nice because that means that a word of length n in the larger alphabet corresponds to a word of length t times n over the binary alphabet. So there's a factor, a blow-up factor of t, but t is log base 2 of K, which is a constant, okay? And what I mean by a constant is that this is a number that does not depend on the length of the string. No matter what the length of the string is, this t is always going to be the same. And this constant blow-up factor is not important, right? So what's a constant factor between friends? In theoretical computer science, we really don't care about constant factors, okay? And the 2 here, why it's log base 2, is because we're going down to a binary alphabet. So if sigma prime here was size 3, then this would be log base 3 of K. Good. So now, but about unary though. So it seems like if we're talking about larger alphabet going down to a binary alphabet, no problem, totally fine. But what about unary encoding? So let's look at the natural numbers as an example. In binary, we have some encoding, good. And in unary, we would encode it like this, okay. But how do the lengths of these encodings now differ, right? Binary versus unary. So a number, natural number n, has length about log base 2 of n in binary. I mean, you don't have to know this formula, the floor of log base 2 of n plus 1. I don't remember that either. But I know that it's like log base 2 of n pretty much, right? And in base k, this would be log base k of n. But in unary, the length of the string is n. So how do these lengths compare to each other? First of all, log base 2 and log base k of n, probably you know this formula, right? So log base k of n can be written as log base 2 of n divided by log base 2 of k. So there's a factor, this is the factor between log base k of n and log base 2 of n. And again, this is constant, so it's okay, it doesn't matter. On the other hand, unary is different, right? So the relationship between log n and n is the same as the relationship between n and exponential in n, right? 2 to the n. So unary is exponentially longer than other bases. So for example, let me write here like log base 2 of n, compare that to n. So if log base 2 of n is 3, n is 2 to the 3, 8. If it is 10, then it's going to be 2 to the 10, which is about 1,000. If it's 300, which is a small number, peanuts, it's going to be 2 to the 300. And 2 to the 300 is the number of particles in the observable universe. Okay, so already like we're at a humongous number. And if it's like 1,000, I mean, I don't know, 2 to the 1,000, like we don't have enough space in the universe to like hold like that many symbols or things, right? 2 to the 1,000, for example. in a lot of the cases, we just use base 2 binary. It's convenient, but you don't want to go to unary. Unary can be exponentially larger, and that's not a good way to represent information. Okay, so now which sets are encodable? We talked about this. Encodability actually is equivalent to countability, and it's actually the right way to define countability, in my opinion. I'll say more about that. But for now, don't worry about this. We'll see this later. Now, you might ask, though, at this point, what about uncountable sets? Like, what about the reals? How do I encode the reals? Well, yeah, you can't, okay? But what do we do? How do we deal with reals? Right? You can give up, you can cry, but yeah, so approximate, right? Well, what else can we do? Some kind of approximation, right? So you give me enough decimal points. After some point, you gave me enough precision that, I don't want more information about the real number, right? So that should be enough to do my computation. Okay, so a summary so far is the following. So we have alphabet, the notion of an alphabet, finite non-empty set, string, a word over the alphabet, and sigma star is the set of all finite length strings over the alphabet sigma. The encoding of a set is an injective function from A to sigma star. Encodability turns out to be equivalent to countability. We'll come back to this point later. Just keep that at the back of your mind for now. Don't worry too much about it. And the alphabet doesn't matter much as long as you're not using unary, right? So as long as you have binary or higher, you're good to go. Okay, so now we want to understand computation. We want to understand what an algorithm is. We want to understand mathematically how to represent these things. And we've now seen one piece of the puzzle. Okay, so input data, output data for us is input string, output string, right? So we're going to represent data as strings over some alphabet of our choosing. Good. Now we want to go to the next step and try to, figure out the other pieces of this now. Okay, so we're going to do some groundwork here to motivate some of the definitions. And then really starting next week is when we're going to really get into this in more detail. Okay, so now I want to, represent computation formally, mathematically. And it's like, it makes sense to actually, make some reasonable assumptions to start with. You don't want to maybe go with, the most general thing you can possibly think of at first, but make some reasonable restrictions that will help you with your modeling phase, and then you can add on to it later, right? So one reasonable assumption I think is a good assumption to make to begin with is that the computer is deterministic. Now, of course, you can say, hey, we have randomized algorithms and non-determinism. Absolutely, yes. But, at first, when I'm just like trying to initially formalize computation, it's better to just let's do it for deterministic first, and then we can add like, randomize. How can I add to my model for deterministic computation? Randomization. Okay, and what deterministic means is basically given an input string, the computer will always produce the same output. Okay, and so in that sense, it's deterministic. Okay, what else can I say? Well, I'm going to assume the input can be any finite length string. Now, it's possible that the finite length string that you give it is kind of gibberish. It doesn't correspond to the valid encoding of anything meaningful. That's okay. We can still feed this kind of string into the computer. And if the computer cannot understand it, like does not know what this thing corresponds to, then it will just say, I don't know what this is, gives you an error or something. But, we'll allow any input, any finite length string as input. Also, we're going to assume for all inputs, there's going to be an output given by the computer. And we're going to assume that the output is a finite length string. Of course, there are reasonable ways to talk about outputs, infinite length outputs from a computer. And that's fine, but like initially, I think when you're modeling this, I think it's a good starting point to think about just like it's going to be a finite length string output. and that will be the model. Okay. Our computing model will allow infinite loops. That's not a problem. Okay, so now given these, how can we characterize the input-output behavior of a computer? Okay, so given these assumptions to start with, what kind of mathematical object characterizes the input-output behavior of a computer? Yeah, exactly. It seems like it's a function, right? So it's a function in particular from sigma star to sigma star. It's mapping input strings, finite length strings to finite length strings. So then, question is a computer just a function from sigma star to sigma star? Right? That's the question. What do you think? Should we define computer as a function from sigma star to sigma star? Why is that not a satisfactory definition? The issue here is computation is not about what, it's about how. It's not, so when we're defining computation, we don't want to know just like what input maps to what output. We want to know how do you go from the input to the output? What is the process that takes you from the input string to the output string? And formalizing computation is about formalizing that process that takes you from the input to the output, okay? And a function does not tell you what the process is, it just tells you for this input, the output should be this, okay? So that's a distinction, an important distinction here. But this is still a good thing to define formally. I think we have identified something interesting that needs a definition. And this is actually called a computational problem, or in this particular case, a function problem, okay? So a function problem is a function of the form sigma star to sigma star, okay? And then we'll say that if the input-output behavior of a computer matches exactly the function problem you have, then that computer solves that function problem, okay? So as an example, you might have the multiplication problem, right? So that's a function problem. And if you have a computer whose input-output behavior matches the multiplication problem, then that computer solves the multiplication problem. But for a computer, what's important, of course, is how do you go from the input to the output? We have to specify the process of that, okay? So let me give you some examples of function problems. Reverse function. So like we're going to fix the alphabet to be 0, 1. So in the reverse function, you take a binary string and you reverse it. That's a function problem. A sorting function. You have some string, you put the zeros in front of the ones. Okay, so that's some sorting function. Is prime. So you're given some number in binary, you want to know whether it's prime or not, and if it's not prime, you output 0. If it's prime, you output 1, okay? So in this case, this number is 250, so that's not prime. This number is 251, and that is prime, okay? So, yeah, and the last one here is interesting because in the last one, the output is always a length 1 string. It's either 0 or 1. So it's like a yes/no question. And we'll talk about that in a second, but it's a kind of different than the other ones. Okay, so now this being said, right, so I gave you some examples of function problems. This is not really the typical way we represent or communicate with each other what a function problem is. Like the common description that I might give you for is prime, let's say, would be, hey, this prime problem is the following. Given a natural number n, output true if n is prime and output false otherwise. So in particular here, the input type is a natural number and the output type is a Boolean. And this is the way I would describe a problem, a computational problem to you. Right, so in general, really, when we communicate or when we think about problems, computational problems, we might be thinking about a function, a general function from a set of instances, a set of possible inputs, to a set of solutions, which is S, okay? And in particular, the set I, the set of instances and the set of solutions, they're not necessarily strings, right? So they can, like as we said, the instance set can be natural numbers, the solution set can be a Boolean, for example. So this is an example, for instance, going from instance to solution, right, is prime. Here's the instance set is the natural numbers, the solution set is no, yes. Here's the addition problem. The instance set is tuple of natural. So I'm here restricting addition to just natural numbers. And the solution is another natural number. It could be sorting. So the instance set consists of, let's say, tuples of strings or like lists of strings. And then the solutions are the also sorted lists of strings. Right, so now when we want to view this kind of function problem, computational problem, in terms of mapping strings to strings, what we will do is use encodings, right? So we saw encodings. In TCS, in theoretical computer science, we only have one type of data, which we only deal with strings. Our formalization is going to be only with strings, not with arbitrary data. And to view this kind of thing as mapping strings to strings, we're going to take the instance set, we're going to encode it, and we're going to take the solution set and we're going to encode it. And then we're going to define f prime based on those encodings, right? So the way basically this would work is as follows. It's like exactly what you expected, right? So nothing fancy here. So you have your original, function problem mapping arbitrary instances to solutions. You want to view this as mapping sigma star to sigma star. So you take your elements of the instance set and you encode them, right? And you have some encoding here, enc. You do the same with the solution set. You encode the elements of the solution set one by one. And then you can define now your mapping from sigma star to sigma star in the way that you expect. There's a technicality alert. This is not, so this is almost good, but what is one potential problem here? F prime is not quite well defined yet. Very good. So what about strings in sigma star that don't have a valid encoding, right? So suppose now I have a string here, okay? And as you can see, this string in sigma star is not a valid encoding of anything in the instance set I. And now I have not defined for you, I did not tell you, where does this go? What does it map to? So this is not well defined until I tell you what happens to these kinds of strings. And this is not an issue. Like we basically say, well, if it's not a valid encoding of some instance, fine, just map it to some, identify maybe some kind of a string here that maybe is like an error string or something like this, right? So we can deal with this. It's not a big deal, okay? But this is the general idea. And here's the thing to keep in mind, important. In theoretical computer science, there's only one type of data, okay? So this is very nice. We boil down everything to one common type, and that unifies everything for us, which is desirable. And it also actually gives us a notion of length of an input, right? So now we look at the string representation, and the length of that string gives us a notion of length. And that's very important when we talk about computational complexity theory, because we're going to look at the running time algorithms, how they scale with respect to input length. Okay. Okay, so now there's a convenient restriction that I want to tell you about, which is a restriction that we're going to be applying in the beginning of the course. And this is, we're going to restrict ourselves to function problems, computational problems with two possible solutions, okay? Just like is prime. And these are called decision problems, problems with just a yes-no answer. And we're going to denote these mathematically as just a function from sigma star to 0, 1. But 0, 1, that's an arbitrary choice. You can think of this as false, true, reject, accept, no, yes. Doesn't matter really, right? The essence is that these are yes-no questions. And is prime is a good example of this, right? Given a number, is the prime number or not. Now, why do we do this restriction? And why are we okay or happy with this restriction? There are a couple of reasons. So one, I would say decision problems are sort of simpler objects compared to more general function problems, more general computational problems. And it turns out it's most of the time without loss of generality. Okay, so let me expand on these 2 points very quickly. So decision problems are simpler objects, and it turns out they are basically equivalent to just a set of words, a set of strings. And let me tell you why or how that is the case. For this, I need one definition. So we're going to define now the concept of a language. Okay, so this is again a technical term that we're defining. A language is any basically subset of sigma star, or in other words, any set of finite length strings is called a language. Here are some examples over the binary alphabet. So the empty set is a subset of sigma star. It's a language. The whole sigma star, the set of all finite length strings, that's also a valid language. A finite language like 0, 1, 0, 0, 1, 1 with 4 strings in it, that's a language. Or it could be like infinite something like this, empty string 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on. That's also a language. Okay, so this is the concept of a language. And the reason I define this concept to you now is because this is the same thing as a decision problem. A language and decision problems are basically the same thing. We think of them as the same thing. So there's a one-to-one correspondence between decision problems and languages. So a decision problem is really a set of words. Why? Because let's say you have some decision problem, sigma star to 0, 1. Okay, maybe you write it out like a table like this, instances mapping to solutions. Now, what do you think is the language corresponding to this decision problem? How are we going to define it? Yeah, everything with a 1, right? Any string that maps to a 1 is going to be the stuff in the language, right? So L in this case is going to be the empty string, the string 0, the string 1, 0, 0, 1, 1, 0, 0, and so on. Okay? So a good picture maybe to keep in mind is the following. Okay, so when you have a decision problem, that maps finite length strings to 0 or 1. So right, here's the mapping. Now just look at all those strings that map to 1, and that's your language L. And similarly, if you give me a language, a set of strings, then I can create the corresponding decision problem very easily. I'll take all those words in L, map them to 1, and everything not in L will map to 0. Right? So in this sense, there's a one-to-one correspondence. And we will go back and forth between these two things very freely. Decision problem, language, they're the same thing. Okay. Now, the other thing I want to say is that this is kind of without loss of generality, this restriction that we're applying and just looking at decision problems, because it turns out in most cases, if you give me a function problem, I can find a corresponding decision problem that is roughly equivalent to it, in the sense that if you can solve one efficiently, first of all, if you can solve one, you can solve the other. And if you can solve actually one efficiently, you can solve the other efficiently as well. So in this sense, there's an equivalence to them. Okay, so here's an example of this. Integer factorization problem. You are given a natural number n, and you want to output the prime factorization of n. So this is a function problem, right? Not a decision problem, a function problem. And here is the corresponding decision version of this. You're given now natural numbers n and another one k. And you want to now output true if and only if n has a factor between 2 and k. Okay? All right, so now, hopefully it's clear that if you give me a solution, if I can solve the integer factorization problem, then I can solve the decision version as well. Right? So if I can find the prime factorization, then I can look at the smallest prime factor and check is that between 2 and k, and I can solve the decision version. It turns out the other way around is also true. If you can solve the decision version, you can also solve the integer factorization problem efficiently. Okay, so does anyone see How can you go from a decision version to an integer factorization problem? Yeah, so let me help you with this a little bit. So here's an intermediate problem that you can use, right? So we talked about going from integer factorization to decision. So now we want to go the other way. And I'm going to add an intermediate problem here. Consider the smallest factor problem. Given a natural number n, find the smallest factor of n. Now, can you go from here to here, the second level, from decision version to smallest factor? And then can we go from here to here? Right? Yeah, so good. I'm seeing some good examples. So good ideas here. Very nice. So first of all, let me talk about this arrow, the top arrow. If I can find the smallest factor, can I get the integer factorization from that? Yes. Why? Because I'll find the smallest factor of the number, and then let's say it's like 5, and then I'll divide the number by 5 and then repeat with that number. So I can just peel off the smallest factor one by one. It's going to be a prime number, and get the prime factorization that way. And how can I go from the decision version to the smallest, this one here? Yeah, so you can basically, I mean, I've seen binary search, absolutely right. So you can do, using the decision version, you can do a binary search by playing around what the value of k is. Like you can set k to be n over 2 and say, oh, is there a factor between 2 and n over 2? Yes, okay, is there a factor between 2 and n over 4? And this way you can pinpoint exactly what factor you have. Now you don't have to start with n over 2. It turns out you can start with the square root of n, but okay, so that's not too important. It doesn't change the complexity too much. Okay, so that's basically an idea about how like function problems and their corresponding decision problems, most of the time they're equivalent with respect to computability, even with respect to complexity of the problems. So then it is nice to just restrict our attention to these yes-no questions, which are simpler objects. And by studying these yes-no questions, we are really studying computation more or less in its full generality. Okay? So, and decision problems, as we said, are languages, right? So we're really going to be studying for the first, well, for most of the course, just like languages and decision problems. So questions that we're going to be looking at, are all languages computable or decidable? Another word for it. Are we going to ask, how can you prove that if a language is not computable, how can you prove that it's not computable, or how can you show it's undecidable? How do we measure the complexity of algorithms that decide languages? How do we classify languages according to the resources needed to decide them? So now this is in the complexity theory territory. The famous P versus NP problem, you may not have noticed this, but P and NP are actually two sets, and they are sets of languages. P is a set of languages defined in a certain way, and P is a set of languages defined in a certain way. And the question, the famous P versus NP question, is asking whether these two sets of languages are the same or not. Okay, and we'll see that.